if you watch the videos that I posted from Math is Power for You, they actually go through both methods. They go through the method where you can change limits of integration and where you don't change limits of integration. And he's very clear about why, when you do either one, why you have to change the limits of integration and how you can get away without changing them. He's very clear about that. So I really do like those videos a lot more for explaining this part. Okay, so remember, when we're doing an integral, why did we start with the antiderivatives in this lecture? Because the basic thing with integrals is you want to use the fundamental theorem of calculus, right? I need to find an antiderivative of this function first, and then substitute the top and bottom numbers. However, we're going to use that substitution to also change the numbers. So let's focus on the antiderivative first. What would you let u equal here? Pretend you didn't have those numbers, and you just wanted to find the antiderivative of this function. What would you make your u here? X to the fourth plus 1. Good. A few people said that, right? Its derivative is 4x cubed, and a multiple of 4x cubed is sitting outside. So that's a good choice for you. Now we make the translation table. Okay, so our translation table, as before, starts with I write down my u, I write down my derivative, and then I solve algebraically for dx. But now, when I have numbers in my integral, right, when I have limits of integration, now my translation table gets expanded. Because now I need to figure out what are the new limits of integration. Now, the old limits of integration, like I said, this integral really looks like x equals 0 to x equals 2, right? Those are in disguise values of x. So I have x equals 0 and x equals 2. I want to somehow get x equals 0 to become u equals something, and x equals 2 to get u equals something, right? I want to change those values to be values of u. How do I change x equals 0 and x equals 2 to equivalent values of u? How do you think I would do that? Plug into du dx and solve for u? Not quite. If I plug in x equals 0 into this, I get du dx equals 0. Does that tell me anything about u? No, it tells me the derivative of u. It doesn't really tell me about u. See, so Jonathan, Emily, and Alicia said use u equals x to the fourth plus 1. Plug into u equals x to the fourth. Right, exactly. I actually use the first equation, right? I mean, it's staring you right in the face, right? U equals some function of x. Okay? So I substitute x equals 0 into this, and I get u equals 0 to the fourth plus 1. So I get that u has to be 1. Similarly, for 2, I get that u equals 2 to the fourth plus 1. So I get 17. And those are my new values, right? Now let's translate. Okay. So as before, we translate each individual part of the integral. Right, the x cubed, I'm still not sure what to do with it, so I'll leave it alone. The x to the fourth plus 1, that's u to the 1/3. And the dx, according to my translation table, is du over 4x cubed. Now, at the same time, I am also writing my new numbers. And I'm going to put here, I'm going to remind you that this really is saying x equals 0, x equals 2. This is going to be u equals something, or this is u equals 1 and u equals 17. It actually is important right now that I do the u equals because my integral is still kind of has mixed variables. All right, so now the x cubed cancels out. Very good. And I'm left with the following. 1/4 u to the 1/3 du, and the integral goes from 1 to 17. Notice I have now dispensed with the u equals because my integral is now only in terms of u anyway, so I don't need to remind you that those are numbers for u. It's understood. Okay, but now I'm ready to do fundamental theorem of calculus. Now, fundamental theorem of calculus tells me the constant comes along for the ride, the 1/4. Then I increase my exponent by 1, and I divide by the new exponent. And it is very, very important here, right? This is fundamental theorem. We do not go back to x. Right? The whole point of the substitution rule is to make the original integral look simpler. Right? I think you should agree that the second integral in terms of u looks a lot simpler than the original. So once you have a simpler integral, once you get down to this thing right here, this boxed thing, all of this doesn't matter. Who cares? Who cares where it came from? This is as if you were restarting the problem and I said, calculate this integral. Well, for that, you just do fundamental theorem of calculus, plug in the two numbers, and that's it. Right? Remember, the final answer is a number. It's not in terms of x. So whether this came from a different variable like x is immaterial, right? The final answer is going to be a number. So what do we get here? So I substitute, so the 1/4, actually, let's just clean this up. So I get 3/16 u to the 4/3, plugging in 1 and 17. So I get 3/16 times 17 to the 4/3 minus 1 to the 4/3, which is just 1. So that would be my final answer. I mean, it's ugly number, but whatever. And if you've taken this course before, you know that I have kind of a little thing to remember here. No more x, only u, which I always say is both good math advice and good life advice. So any questions about that? See a few people typing. What's the reason for not plugging in x? Well, because I don't need to. Where would I plug in x? So you should answer that question first. Where do you plug in x? The final answer has to be a number, right? The final answer is not a function of x. The problem is to find the area under this graph from 0 to 2, right? Calculate this integral. The answer is a number. There's nothing to rewrite in terms of x here. Once you have it in terms of u, this is just like I said, once you have it in terms of u, don't look back, right? Because now all I have to do is find the antiderivative and plug in the two numbers. Why would I go back to x? I mean, the whole point of this, think about what you would be doing if you went back to x. If I wrote now here, okay, this is 1/4, or rather 3/16, x to the 4th plus 1 to the 4/3, and then go back to the original numbers, 0 and 2, what would you be doing? All you would be doing is plugging in 2 and 0 again, just to get back 1 and 17. I mean, you're undoing your work just to rewrite it another time. And you're missing the whole spirit of the problem, right? The whole spirit of the problem is that the u substitution makes the problem easier. Believe me, this is it's a very common thing for, I mean, when I say very common, I mean like almost like a quarter to half the students kind of go back to x. Or another thing students will do is they'll go back to x but not change the numbers back, or something like that, right? Plug in the wrong numbers, but there's no reason to go back to x. That's a good question. I'm probably going to be reminding everyone of that often. Well, for normal antiderivatives, you would go back to x. Like, for instance, if I just scroll back to, say, this part, find this antiderivative. The reason why I went back to x is because this is not asking for an integral. This is not asking for area under a graph. This question is literally asking, give me an antiderivative of this function in terms of x. So the answer should be a function of x, right? Antiderivatives, indefinite integrals, what your textbook calls them, indefinite integrals, they ask for two different things, right? One asks for a number, the other one asks for a function of x. So it does make sense to go back for this type of question.
So thanks. So the final way that you have it written, Can we just leave it like that, or do you want us to like
How else would you like to write
simplify
this?
it?
How else would you like to write this? Do you 17 to the 4/3 is 17 to the 4/3. That's it.
I mean, okay.
That's it.
Thanks.
Yeah, no, good question, Bennett. Honestly, what John and Bennett asked, I'm probably going to repeat those questions and answers several times. I'm going to sound like a broken record at some point.